Scientists are using the new James Webb Space Telescope, JWST, to study Neptune's largest moon, Triton, for the first time. Unlike older telescopes, JWST can see infrared light which is invisible to our eyes. This light can reveal the makeup of Triton's surface, its atmosphere, and even hints of a hidden ocean. Could JWST take pictures of Triton's surface? What is Triton's surface made of? Does it have an atmosphere? Is there a hidden ocean under the ice? Could there even be life on Triton? JWST may help us answer these questions and more, but for now you'll have to stay tuned to learn the full story. Triton, Neptune's largest moon, is like a distant enigma in our cosmic backyard, wrapped in a chilly blanket of nitrogen and reflecting a large portion of the sunlight that hits it. Triton has always intrigued astronomers, but with the arrival of the James Webb Space Telescope, it's as though a new dawn has emerged in our quest to understand this icy world. Think of JWST as our cosmic detective, but with a twist, it sees things in a different light. Instead of just regular visible light, JWST specializes in the infrared spectrum, which is like having a superpower to see things in a new way. While JWST can't snap Instagram-worthy photos of Triton's surface like a rover would, it can analyze the infrared light bouncing off Triton, providing a sneak peek into what the moon is made of, how hot or cold it gets in different spots, and what kind of atmosphere it has. Picture JWST as an artist. Instead of using colors, it uses different shades of infrared to create a detailed picture of Triton. This isn't just any painting. It's like a masterpiece that could uncover hidden secrets lurking beneath the surface. With JWST's infrared gaze, we might finally unravel the mysteries of Triton's terrain, spot strange formations, understand its weather patterns, and even catch clues about what's happening under all that icy exterior. Who knows? We might stumble upon signs of bubbling activity or hidden oceans, transforming Triton from a distant curiosity into a world full of surprises. Imagine Triton as a colorful map, with each color representing a different frozen ingredient like nitrogen or methane. JWST can read these colors like a book, telling us stories about Triton's past. For example, it might reveal if Triton was struck by big space rocks or had icy volcanoes erupting. JWST might even spot areas with a lot of methane ice, hinting at old cryovolcanoes spewing out frozen gases. Triton's chilly air, mostly nitrogen, is also under JWST's watchful eye. The telescope can see where sunlight sneaks through and turns ice into gas, similar to watching steam rise from a cup of hot cocoa on a frosty morning. Thanks to JWST, Triton isn't just a boring old frozen moon. Gases like methane or carbon monoxide could be clues to some serious underground action, such as plumes of warm water sneaking out from beneath the icy surface. But the real jackpot could be what lies beneath Triton's icy shell. Some scientists believe there might be a secret ocean hiding underneath, kept cozy by Neptune's gravitational embrace. Although JWST can't peek directly at this ocean, it's on the lookout for clues. For instance, if JWST spots a hot spot on Triton's surface where there shouldn't be one, it could be like finding a warm spot on an icy pond, potentially indicating that water is bubbling up from below. While JWST can't solve the mystery alone, its findings may lay the groundwork for future missions to confirm the ocean's existence and learn what might be inside it. The observations from JWST are likely to be a game-changer in our understanding of Triton. Let's discuss why. Compositional diversity * JWST's detailed mapping of Triton's surface ice could reveal a more complex composition than we previously thought, including pockets of exotic ice that may point to past collisions or interactions with comets. Atmospheric dynamics * studying the movement of trace gases in Triton's thin atmosphere could provide clues about potential cryovolcanic activity and the influence of Neptune's gravity. Evidence of cryovolcanism * detecting methane or other gases associated with volcanic activity would be groundbreaking, suggesting that geological processes are still occurring on this icy world. Subsurface ocean clues * identifying regions with unusual heat signatures or wobbliness in Triton's rotation could hint at the presence of a hidden ocean, paving the way for future missions to confirm its existence. Triton holds the key to unlocking not just its own mysteries but also broader questions about the entire solar system. How can JWST's observations impact our understanding? For example, the origin of Plutoid's asterisk Triton's composition and geological activity could shed light on the origins of Pluto and other Kuiper Belt objects, KBOs. Were they formed in the same region as Neptune, or did they migrate from elsewhere in the early solar system? Understanding Triton's history could help piece together the formation and evolution of these icy worlds. Habitability of icy moons asterisk. If JWST provides evidence of a subsurface ocean on Triton, it would strengthen the case for the potential habitability of other icy moons in our solar system, like Europa and Enceladus. Studying Triton's potential ocean composition and its interaction with its rocky core could inform future missions searching for life in the outer solar system's icy realms. Cryovolcanism and organic molecules asterisk. Cryovolcanic activity on Triton could potentially release water ice mixed with organic molecules, the building blocks of life. Studying the composition of these plumes, either directly or through the analysis of atmospheric trace gases, could offer valuable insights into the potential for prebiotic chemistry on icy worlds. Despite JWST's incredible potential, there are challenges to overcome. Triton's vast distance from Earth limits the resolution of JWST's observations. Additionally, the faintness of Triton's reflected light requires long exposure times, making it difficult to capture rapid changes in its atmosphere. However, JWST is just the first step. Future missions leveraging JWST's findings could revolutionize our understanding of Triton. An orbiter specifically designed for Triton could map its surface in high resolution, study its atmosphere in detail, and potentially detect plumes or other signs of geological activity. A lander could provide in situ measurements of the surface composition, search for signs of past or present water, and potentially sample any plumes that erupt. A combination of an orbiter and a lander would offer the most comprehensive picture of Triton, allowing for simultaneous study of its surface, atmosphere, and potential internal processes. The James Webb Space Telescope boasts a suite of cutting-edge instruments specifically suited for studying distant, faint objects like Triton. Here's a closer look at some key players. Near-infrared camera, NIR-CAM. This powerful camera operates in the near-infrared spectrum, allowing it to pierce through the haze surrounding Triton and capture faint light reflected from its surface. By analyzing the intensity of light at different wavelengths, scientists can identify specific molecules present on the surface, creating a detailed compositional map. Near-infrared spectrograph, NIR-SPEC. This instrument acts as a light detective, breaking down the infrared light from Triton into its component wavelengths. This spectrum reveals unique fingerprints of different molecules, allowing scientists to identify the materials present, determine their abundance, and even assess their temperature. By observing variations in the spectrum across Triton's surface, scientists can map out temperature differences and potentially identify regions with anomalous heat signatures. Mid-infrared instrument MIRI, operating at longer wavelengths. MIRI can peer deeper into Triton's atmosphere and potentially detect trace gases like methane or carbon monoxide. These gases might be signatures of ongoing geological activity, offering clues about potential cryovolcanism. Additionally, MIRI can probe the faint thermal radiation emitted by Triton itself, providing insights into its overall temperature and any internal heat sources. Reaching Neptune and Triton presents a formidable challenge. The vast distance, roughly 2.8 billion miles from Earth, translates to a travel time of over a decade using current propulsion technologies. Additionally, the faint sunlight at Neptune's distance makes it difficult to generate enough power for traditional spacecraft operations. To explore Triton, we have different mission options, including using gravity for speed, nuclear power for energy, or smaller probes for specific tasks. However, we must be careful not to contaminate Triton with Earth germs and ensure we understand what signs of life there might look like. Balancing exploration with protecting Triton's potential for life is crucial. As we delve deeper into the possibilities that JWST presents for understanding Triton, it is crucial to explore the broader context of how these observations fit into our larger exploration of the outer solar system. Triton is not just a fascinating object in its own right, but a valuable puzzle piece in understanding the formation and evolution of moons and planets throughout the solar system. By closely examining its characteristics, scientists hope to gain insights that could affect our broader understanding of planetary science, the behavior of icy moons, and even the potential for life in other corners of the universe. One key aspect of studying Triton is its unique orbital behavior. Triton is thought to be a captured moon, possibly once a part of the Kuiper Belt, which now follows a retrograde orbit around Neptune. This unusual orbit could help astronomers understand the dynamics of Neptune's gravitational influence, as well as the processes that might have occurred when Triton was captured. Understanding these dynamics is not only important for Triton itself, but also for studying the formation and migration of other moons in the solar system. Triton's retrograde orbit makes it an intriguing target for studying planetary capture and the history of Neptune's gravitational influence on surrounding bodies. If Triton was originally part of the Kuiper Belt, its capture by Neptune could have been a dramatic event, and the moon's current orbit may be a result of this dynamic process. This understanding of the moon's orbital history can help planetary scientists understand the behavior of other moons that orbit giant planets in the outer solar system, including the ones that circle Saturn, Jupiter, and Uranus. In addition, studying how Triton interacts with Neptune's gravity could also provide valuable insights into the evolution of Neptune itself. Beyond Triton's orbital peculiarities, its surface features also offer significant scientific potential. JWST's ability to analyze infrared light allows scientists to investigate the composition of Triton's surface, revealing important clues about the processes that have shaped it. For example, the presence of nitrogen and methane ice on the surface could indicate the presence of active cryovolcanism, volcanic activity that involves the eruption of water, ammonia, or methane instead of molten rock. This kind of volcanic activity may not only tell us more about Triton's geological history, but could also provide further evidence of subsurface processes, which could be crucial for understanding the potential habitability of icy moons in the outer solar system. In addition to its surface composition, Triton's atmosphere is another intriguing feature that JWST will be studying. While Triton's atmosphere is thin, it is still composed primarily of nitrogen, with traces of methane and other gases. The thin nature of this atmosphere, combined with the extreme cold temperatures near Neptune, creates a unique environment that may help researchers understand the atmospheric processes of other distant moons and planets. By examining Triton's atmosphere in detail, JWST could reveal how the interaction between the moon's surface and atmosphere might work in such a distant and cold environment. Scientists are particularly interested in understanding the seasonal changes on Triton, as its orbit around Neptune is highly tilted, meaning that the seasons are much more extreme than those we experience on Earth. These seasonal shifts could provide important data about the complex interplay between a celestial body's surface, its atmosphere, and its environment in the larger context of the solar system. Triton's potential for harboring life is another key area of interest for scientists. If JWST can detect signs of an ocean beneath the moon's icy surface, this would elevate Triton to the same level of interest as other moons like Europa, Enceladus, and Ganymede, moons that have shown the potential for subsurface oceans. The idea that liquid water could exist beneath the frozen crust of Triton opens up the possibility of an environment that could support life. While this remains speculative, the study of potential subsurface oceans is critical for astrobiology, as scientists look for environments that could have the necessary conditions to host life. JWST's observations could provide some of the first concrete clues about whether such environments could exist on Triton, providing a stepping stone for future exploration missions. In addition to its search for signs of life, JWST's study of Triton will also contribute to our broader understanding of the outer solar system's formation. Triton is believed to be a captured object from the Kuiper Belt, and by studying its composition, scientists can learn more about the conditions in the early solar system. Understanding the materials that make up Triton, whether they are similar to those of other Kuiper Belt objects or different, could reveal new information about the processes that shaped the outer regions of our solar system. By analyzing Triton's surface and atmosphere, JWST can help us understand the conditions in the early solar system that led to the formation of distant objects like Triton, Pluto, and other icy bodies. Beyond its direct observations, Triton's study through JWST also provides valuable lessons in the exploration of distant worlds. As technology continues to evolve, future missions to distant objects like Triton will likely be able to take advantage of the wealth of information JWST provides. Understanding Triton's surface, atmosphere, and possible internal structure will inform mission planning for landers, probes, or even crewed missions in the future. Moreover, JWST's role in this process is part of a larger shift in space exploration, where telescopes, spacecraft, and rovers work together in a complementary way to gather data from multiple angles. By combining different types of observations, scientists can piece together a more comprehensive picture of Triton and its place in the cosmos. Looking to the future, it's clear that Triton will remain a key focus for astronomers and planetary scientists for years to come. As JWST continues to provide unprecedented insights into this distant moon, its observations will undoubtedly shape the direction of future missions and inform our understanding of the outer solar system. Whether it's finding evidence of cryovolcanism, detecting trace gases in the atmosphere, or uncovering the possibility of a subsurface ocean, JWST's findings will be instrumental in unlocking the many mysteries of Triton. While we are still far from understanding the full scope of what Triton has to offer, JWST has set the stage for a new era in our exploration of the icy moons and distant planets that make up the outer reaches of our solar system.